Hello guys, welcome to our class for today. This Nobleman Science Tutors Online, and for our class for today we are going to be looking at the transformer. We're going to be looking at the transformer, and under this topic we'll look at the transformer, the structure of the transformer, the principle of the working of the transformer. We'll look at some equations that we can use to solve some problems that has to do with the transformer. We have different types of transformer. There are two types of transformer that we'll look at. Then the energy loss in a transformer and how to prevent it. Then we'll now solve some problems, right? We'll solve some problems relating to transformer. So guys, please get your writing materials ready so that we can go straight to our class for today. Well, please, before we go, if you have not subscribed to our channel, please subscribe to the channel. Click on the notification bell so that whenever we upload a new lecture, YouTube will notify you, right? If you have any challenge, you can reach us through the WhatsApp number that is showing right on your screen. So this is your online physics tutorial, and we want to go straight to the class for today. So I hope you are ready and you have gotten your writing materials with you. Please always ensure that you try as much as possible to avoid distractions so that you can focus and then concentrate on the class. All right, so we'll go straight to our class for today. As I said, we are looking at the transformer. So if you are ready, please let us go. Okay, so from time to time, and even in your locality or in your environment, you see transformers that are installed in different locations, right? And you, in most cases, we just see the box structure and we don't know what is inside the box, but we know that okay, this is a transformer, and that whenever they bring light, this transformer might bring down the voltage, and then it will not supply us, which are the consumers. Okay, so sometimes you hear that, oh, a transformer is a step down transformer or it's a step up transformer, as the case may be, but you might not know how it is constructed or what is inside the transformer or even how it works. All right, so it is good as a physics student for you to understand the working principle of that box that you see in your environment or in your locality. Is that okay? So that when you are talking with your friends, you talk like a science student. All right, so the transformer basically is an electrical device uh, for changing the size of voltage, right? So yes, it is used to change the size of voltage, right? It is either used to increase the size of voltage, or it is either used to what decrease the size of voltage, or the EMF, which is the electromotive force of an alternating current. Okay, so you can use it to decrease the electromotive force of an electric current or of an alternating current, or you can use it to increase the electromotive force of an alternating current. So basically this is the structure of the transformer if you look at it very well. So the transformer actually has like two coils. Okay, these are two coils. This is one coil and this is another coil. This one is the primary coil. Okay, then this is the secondary coil, and this coil that are constructed with wire, they are rounded or wound round a laminated core. So this is the main core of the transformer. All right, so the structure of the transformer, it consists of two separate coils. This is the primary coil, and then this is the secondary coil. This primary coil is where current enters the transformer or voltage enters the transformer. So it is the input winding. This is the input winding, and then the secondary coil is the output winding. And as I said, this coil, they are wound around a soft iron core that is laminated. They are wound around a soft iron core that is laminated. Now, this soft iron core is always used in most of uh, most of electrical devices so that you can increase the magnetic flux on the equipment. So the soft iron core has to increase the concentration of magnetic flux within the core. And as I said, it is laminated. Why is it laminated? It is laminated so as to prevent or reduce eddy currents. Eddy current that are induced in the core. So remember that when we discuss electromagnetic induction, we discuss eddy current. Eddy current is just an opposing current to the force that is producing it. Okay, it's a current that opposes motion. All right, so and because it opposes motion, or it opposes the EMF that produces it, it can lead to heat generation in this system. So when the system is laminated, it reduces the effect of eddy current. Is that okay? So this is just the structure of the transformer. All right, so this is what you see in that box that you see. This is what is actually inside. Though there are some other components to increase the working of the transformer, but this is the main component of the transformer. All right, this is the main component of the transformer. So how does the transformer work? All right, so if you look at this pictures that are down here, this is the one I displayed in the first slide. Okay, so you see there are magnetic flux around each of the core. Okay, so these are magnetic flux that are generated when current enters through the primary. Now this magnetic flux, they are linked. Okay, so you can see the magnetic flux from the primary core down to the secondary core. That's okay. So I want to discuss this shortly. Now, the working principle of this device is that when an alternating current, or an alternating voltage, right, is applied at this primary terminal, it produces an alternating magnetic flux in this soft iron core, which links the secondary core. Okay, this is exactly what you are seeing on this picture. And because of this linkage, an alternating EMF is also produced. An alternating EMF with the same frequency is also produced, or it is induced in the secondary core by mutual inductance. Okay, so mutual inductance is the flow of induced current or voltage in a core due to an alternating or varying current in a neighboring coil. So this is the neighboring coil, and then so this the current alternating voltage is induced in a close by coil. So that is what is called mutual inductance. Okay, so this is the working principle of the transformer, and then the total flux linking the two coils proportional to the number of turns. So what that is telling you that the more the number of turns, the more the flux or the magnetic flux that is linking these two coils. Is that okay? And from our drawing, NP is the number of turns in the primary coil, while NS is the number of turns in the secondary coil. The induced EMF in the primary coil is represented by EP, and then the induced EMF in the secondary coil is represented by ES. Is that okay? So the induced EMF in the secondary coil depends on the EMF in the primary coil, and that's led to the derivation of this equation. The ratio of the number of turns of each of the coil, or the ratio of the induced EMF in the secondary coil to the primary coil, is equal to the number of turns in the secondary coil all over the number of turns in the primary coil. Alright, so and this is also written as secondary EMF all over primary EMF is equals to number of turns in the secondary coil all over number of turns in the primary coil. So please, you have to take note of this. We are going to come to it actually. We'll come to all this equation shortly. in the next slide. Is that okay? So you just have to take note of that, because these are the equations that you are going to use to solve problems when you are talking about transformers. All right, so we'll look at some equations that you can use to solve problems when you're talking about the transformer. Okay, so basically when you are talking about the transformer, there are equations that you need, that you use to solve some questions, some problem. Okay, so we've said that the NS is number of turns in the secondary coil, NP number of turns in the primary coil, and we have talked about the relationship between the EMF and the number of turns. Okay, so the EMF that is generated is directly proportional to the number of turns of that particular coil. So the more the number of turns, the more the EMF that is produced. Alright, so for an ideal transformer that is 100% efficient, but we know definitely that you cannot have a device that works 100%. All right, so but for a 100% efficient transformer, the power developed in the secondary coil is equal to the power developed in the primary coil. Remember, this is also a statement of law of consumption of energy. That's okay. So what that is just telling you that for an efficient transformer, energy is not lost, right? Energy is conserved. Fine. So if energy is conserved, it means that the power in the secondary coil is equal to the power in the primary coil. Now we know that power is given to us. Power is given to us as I times V, right? And this V, this can also be written as I, which is current, times E. Okay, so this equation is what is written here. All right, so this is what we have here. Okay, so this is power in the secondary coil is equals to power in the primary coil, where IS is current in the secondary coil and IP is current in the primary coil. So I hope that one is clear. Okay, so if you understand that, this equation, that is equation 1, you can rewrite this equation to be like that. Okay, you can rewrite it to have this all over that, which is there. You can see it's equal to EP, all right, all over ES. So as the case may be, you can write this equation is same thing as what to have as equation 2. Okay, so this is the same thing as what to have as equation 2, that this. Now remember that in the previous slide we said that the EMF in the secondary coil is equal to the number of turns in the secondary coil, the EMF in the primary coil is equal to the number of turns in the coil. So you can actually relate equation 2 and 3. So if you combine these two equations, you are going to have this as your overall equation. Okay, so you have ES over EP is equal to NS over NP is equal to IP over IS. Alright, so with this, I just said that this is like a general transformer equation, because almost all the equation that you're going to solve that talks on transformer, these are the equations that you're going to use. So take note of this equation, because this equation we use to solve some problems when we get them. Now also for the transformer, the efficiency, remember that efficiency is power output all over power input. So in this particular transformer case, power output over power input times 100% is efficiency, right? So for the case of the transformer, we know that power output is power in the secondary coil and power input is power in the primary coil times 100%. So okay, and now we've said that power is equals to electromotive force times current. So electromotive force in the secondary times the current all over electromotive force in the primary times current multiplied by 100. So all this equation talks about efficiency. All this is efficiency, this is efficiency. So as the case may be, you can use this, You can use this, you can use depending on what you are asked to do. All right, so from these equations above, we can see that the current in the two coils are inversely proportional to the number of turns. Okay, so if you look at it, you see current is inversely proportional to the number of turns in each of the coil, while the voltage is direct proportional to the number of turns. Voltage proportional to direct proportional, current inversely proportional. Okay, so I hope that is clear. I hope that is clear, and if you have understood that, thank you very much. Okay, so basically these are the equations for carrying out any calculations when it has to do with the transformer. So as I said before, we are going to talk about the types of transformers. So we have two types of transformer, and these types of transformer, they derive from the number of turns that are in the primary and on the secondary coil. So we have the first one, which is step up transformer. In the step up transformer, the number of turns in the primary coil, they are less than the number of turns. That is what that means, that the number of turns in the secondary coil, they are more than the number of turns in the primary coil. Okay, that any transformer in which the number of turns in the secondary coil is more than the number of turns in the primary coil is known as a step up transformer. And what does this transformer do? It increases the voltage that is applied. So which means that if you apply a low voltage through the primary coil, it will magnify it. All right, it will magnify the voltage. So, and these are majorly the transformer that are used from the power station. Okay, they use it to step up the voltage. Then as it gets to wherever it is going to, they will use another transformer again. Okay, so in this particular transformer, the number of turns in the primary coil is more than the number of turns, and the number of turns in the primary coil is less than the number of turns in the secondary coil. And also, the current in the primary coil is more than the current in the secondary coil. Okay, so what that means is that the primary current is more than the secondary current, while the primary voltage is less than the secondary voltage for this type of transformer. Alright, so this is a step up transformer. Then the other transformer is a step down transformer. So for a step down transformer, you can see it. The number of turns in the primary coil, they are worth more than the number of turns in the secondary coil. So this type of transformer, where you have more turns, more windings in the primary coil than the secondary coil, is known as a step down what? A step down transformer. So in this particular transformer, the current in the secondary coil is more than the current in the primary coil, and the voltage in the primary coil is more than the voltage in the secondary coil because it is a step down transformer. Okay, so this is a step down transformer, so try and take note of this too. And then the ratio of the number of turns in the primary coil to the number of, the number of turns in the secondary to the number of turns in the primary coil is known as the turn ratio of the transformer. And if you look at this ratio for a step down transformer, it is less than 1, and then for a step up transformer it is more than 1. So this is actually a JAMB question that you can be given, so you can take note of this statement. That statement that you should take note of. Okay, so take note of those statements for JAMB in case you are preparing for JAMB. Yes, you can use this ratio to ask you if this ratio is more than 1, what type of transformer is that? Or if it is less than 1, what type of transformer? It depends, as the case may be. The question can come in different form. Just check up some past JAMB questions, we see questions like that. Okay, so that is for a step down transformer. Now, because the transformer is not 100% efficient, there are energy losses, and energy losses, they arise from different factors. Okay, they arise from different factors. One of them is energy loss due to heat loss. Yes, now, because the primary and the secondary coils, they because the primary and secondary coil have resistance, some energy is lost in the form of heat in the coils. Okay, so this energy can be reduced by using a low resistor coil or thick wires. So energy can be lost due to heat in a transformer. Okay, energy can be lost due to heat in a transformer. Another factor that affect the transformer, that makes the transformer to lose energy, is eddy current. We said that eddy current is an opposing current. It's a current that opposes the EMF that produces it. So energy is lost due to eddy current induced by changing magnetic flux in the core of the transformer. And as I've said before, this eddy current can be reduced by laminating the core. This is a jam question. When I say it's a jam question, these are questions that I've seen. So please, you can go and check, you will see. Right? So that's a jam question. Then you also have energy loss due to hysteresis. Alright, so energy loss, hysteresis is heat in the core of the transformer due to reversal of magnetic field in the core. So that is hysteresis. So this can be reduced by use of special alloy in the core of the primary coil or use of soft iron core. So that's why they use soft iron core in the transformer. So this one you can be asked. Energy loss due to hysteresis in the transformer can be reduced by how? By the use of uh, special alloys or use of soft iron core. Then you have energy loss due to leakage of magnetic flux. Yes, if you look at the drawing of the transformer and where the magnetic flux from the primary is linking with the secondary core, you see that sometimes energy is lost. Okay, energy is lost. Okay, because not all the magnetic flux will link to the from the primary to the secondary, and because all of them they will not be linked to it, then there's leakage of magnetic flux. So some energy is lost due to leakage of magnetic flux. This is because not all the magnetic flux produced in the primary coil are linked to the secondary coil. There are leakages before getting to the secondary coil, and this can be reduced by special forms of coil winding or by efficient coil design. Okay, so this is how you can reduce all these factors that can lead to energy loss in the transformer. So when you see the design of the transformer, you find out that the manufacturers, they put all these factors into consideration before they finish, before the final design of the transformer, and that is why a transformer can work very, very efficiently. Okay, so I think basically these are the information that you need to know when you're talking about the transformer, right? So I think this is where the lecture on transformer ends. But what we want to do now is I want to solve some problems to drive home those equations that we just discussed before. Okay, so please pay attention and then follow through. Then I will give you your understanding question that you will solve for yourself. Right, so let's go. Question number 1. Okay, this is a jam question. So find the turns ratio in a transformer which deliver a voltage of 120 volts in the secondary coil from a primary voltage of 60 volts. Right, so in this particular question, you will be given okay, so in this question you are be giving you, you are giving your secondary voltage is given to you to be equals to deliver a voltage of this from this. So secondary voltage is 120, and then your primary voltage or primary EMF is given to you to be 60 volts, So as I said, it's an objective question in JAM, so it's not something that you really need to waste time on. We said that from that our equation we had that ES all over AP is equals to NS all over NP. So which means we can use this equation to solve it. Can use this to solve this. So which means that we'll have 120, because we're looking for turn ratio, all over 60. So basically you can just divide that out and you have your answer to be what? 2. So why I solved this question is for you to see that once you understand those equations, those simple equations, calculations in transformer, they are not that difficult, right? So that is this. So I'll go to another one. This is question number 2. This question says that a transformer is required to give 120 volts from a 240 main supply. If the primary has 500 tons, how many tons has a secondary? Okay, so this is a NECO objective question actually. So for this place, you have been given it's a transformer is required to give, which means that the give is the output, right? So that is ES, which is the secondary, is equals to 120 volts from a main, which is the primary, from a main. So this from is the primary. So this is one. Sorry about that. So it's 240 volts. Then they are giving that if the primary has 5,500 tons, so N primary is equals to 5,500 tons. They say how many tons has secondary, so NS is what we don't know. Okay, so using those our equation, we'll say ES, sorry, don't mind my writing, over IP is equals to NS all over NP. Okay, so we have ES, we have EP, we don't have NS, we have NP. Okay, so we can actually make NS the subject of the formula, so that, because that's what we're looking for now, number of tons in the secondary is not. So let's just make it the subject formula. If you cross multiply, we'll have that number of tons in the secondary will be equals to this times this all over what? All over that. Okay, so you substitute your value into this equation now. You have NES equals to 120, NP, number of tons in the primary is 5,500 as given to us. Then electromotive force voltage in the primary is 240 from the 240 means. Okay, so work this out with your calculator and then work that out with your calculator. You are going to have 2,750 tons in the secondary core. Okay, so I think this question is really simple and it's something that you can easily relate with. Let's do another one. Okay, so this one says that the current in the primary coil of a transformer is 2.5 amp. If the coil has 50 tons, that is the primary coil has 50 tons, and the secondary 250 tons, calculate the current in the secondary coil. Neglect energy losses in the transformer. is WAEC objective 2. Okay, so this one too, you are giving primary current, which is IP, to be equals to 2.5 amp. Okay, then you are giving the number of turns in the primary to be equal to 50. You are given number of turns in the secondary to be equal to 250 turns. Then you are asked to find the current in the primary, in the secondary, which is IS. Sorry about that. So you are asked to find IS, right? Okay. You are asked to find this. This is what we don't know. So using our equation, from my equation we said that N secondary all over N primary, number of turns in secondary and primary, is equals to current in the primary all over current in the secondary. Remember, we said that the current is inversely proportional. Okay, so that's what we said. Current is inversely proportional to number of turns. So having written this, you cannot make current in the secondary is subject of your formula. Okay, so we make that the subject of a formula so that you have that current in secondary will be equals to NP times IP all over NS. So substituting this equation, you are going to have IP, current in the primary is 2.5, number of turns in the primary is 50, number of turns in the primary is 50, okay, times 50 all over 250. So you can do this division out with your calculator. This will give you 0.5 amps. Okay, so these are simple questions and I hope you follow through with this. Okay, so I hope this is simple and you have followed through. So let's do one more question before we go to your test understanding page. I'm trying to go through the question that I know at least, so I try to vary the questions, and these questions, they are from different years of in WAEC, JAM and this thing. Okay, so this last one is a WAEC question. It's a WAEC theory question, and okay, so this is a WAEC theory question. So this question says that a 95% efficient transformer is used to operate a lamp rated 60 watts 220 volt from a 4400 volt AC supply. Calculate the 1 ratio of the number of turns in the primary coil to the number of turns in the secondary coil. 2. Current taken from the mains circuits. Okay, current taken from the main circuit, the main circuit is the primary circuit, so that should be the primary supply. So this one is a primary current. Okay, so for this particular question, we are given that the efficiency of this equipment is 95%. So this is given to us. Another variable that is given to us is the power, because this is the load. Okay, so it is used to operate this load. So this is the power output in the secondary. So this is power in the secondary coil. So and that is 60 watts. Okay, then we are given the electromotive force or the voltage in the primary coil to be 4400, and then the voltage in the in the secondary coil to be ES is equals to 220 volts. It's equals to 220 volts. Alright, so here we are asked to find the number of turns. Number of turns, the number one is number of turns. Number of turns is given to us to be the ratio all over this. So number of turns in the primary all over number of turns in the secondary will give us 2, 4. Remember that we've used this equation to solve a problem before. Okay, we used it to solve a problem before, so please try to remember this. Okay, so this is exactly what we are using now, so that you will not ask how come I'm using that. Okay, so this, if you do this out, if you work this out, you are going to have 20. So this gives you the number of turns. That is for the number one. Because here they say find the ratio of the number of turns in the primary coil to the number of turns in the secondary coil. Okay, so follow the statement of the equation that is given to you. Alright, because if you look at the equation I gave to you, I said we wrote that number of turns in secondary all over number of turns in primary. Alright, but now they say find the number of turns in the primary coil to the number of turns in the secondary coil. That is the ratio they say you should find, and that is why this equation is now written this way. So be careful before you will start to ask me question. How come you are changing this thing upside down? So please follow through with the equation that is given. Alright, so fine. Then in the second instance, we are given the efficiency. Remember that we said efficiency is equals to what? Power in the secondary, power output all over power in the primary multiplied by 100%. That's what we said. And this can also be written as power in the secondary. Power in the primary is equals to what? It's equals to current times voltage multiplied by 100. So what you are looking for now is the current taken from the main, which is the current of the primary. Okay, so in this question you will be given this power in the secondary is this is power and this is the voltage in the primary, and you are looking for the current. Okay, so you can actually make the main current of supply your solder formula, but before then you can write this as efficiency is given to be 95. So you write 95 is equals to PS, which is power in secondary, is equals 60 all over current in the primary multiplied by the voltage, which is 4400. Everything is multiplied by 100. Fine. So once you have gotten this question, you can make this your subject. So permit me to do this. So we can have that the current in the primary will be equal to, when you do your cross multiplication and you make that a subject, it will be equals to 60 times 100 times 100 all over 95 times 4400. Okay, so by the time you work this out with your calculator, you find out that the current in the primary, so we're looking for, is equals to 0.0144 amp. Okay, so this is a little bit trickish, but it's simple. All right, so I hope you follow through with this and you are able to understand the verse. So the questions that you're going to see, they are not different from what we've done so far. So please let's go straight to your test your understanding page. So this is your test your understanding page. If you look at all these questions, we've solved all of them. Okay, there is no question we've not solved here. All right, so primary winding, this has to do with calculate current in the 240 supply. This is also primary current. All right, so the efficiency of this is similar. So we've done everything. So I want you to please review and solve all this problem. All right, guys. So thank you so much for your time. Thank you for your time and for visiting our channel. This is how we'll continue to roll out lectures for you. Okay, so please continue to visit our channel, and we appreciate you for all your comments and your wonderful for all your wonderful comments. Yeah, but before I leave, please, if you have not subscribed to our channel, please subscribe to the channel, give us a like, give us a thumbs up, and invite your friends. Right, invite your friends. Give us a positive comment. If you have a challenge, reach us through the WhatsApp number that's showing right on your screen. So this is No Math Science Tutorials Online. I remain Otubo Mike. You are welcome to our class, and we hope to see you in our next class. Please do have a nice day and enjoy yourself. Thanks.